All right, first of all, you're just distributing. So you're multiplying through by p to the power of n. I'm going to rewrite this. So you have p to the power of n times the first part, m, plus, and then p to the power of n times the second term. Now, when you multiply power forms, you just add exponents. Hold on. Hold on. That really didn't come out right there. That was supposed to be minus n. Okay, so when you add these, and be careful. You just add an exponent, so the n and the negative n add up to 0, so you have m plus 1. Actually, add exponents. Over here, when you add exponents, the n's 0 out, you're left with just m, and you're done. Now, our goal is to simplify this thing, so we are done. I want to point out one little thing, though. Watch this. This I could rewrite as p to the power of m times p. The plus 1 means you don't have m factors of p, you have one extra. And so you could write it like this. And then, but that means you could actually factor this thing if you wanted to. And both terms have m factors of p. You take them out here, you're left with one more factor of p. You take them all out here, you're left with 1. Now, that wasn't what we're doing here. I'm going to show you that. Now, look at 31. Same kind of situation. You distribute, and so you get z to the power of, and here, I'm just going to add them. N's 0 out, you get m plus m, it's 2m for that exponent. Next one, the n's 0 out, and the m's also 0 out, so you get 0 for the exponent. And the last one, it works out to m. Now let me rearrange this. The 2m I'll put first, then the m, z to the power of m, and then it's minus 1, because the n to the power of 0 is 1. And you can't do any more. One thing I want you to appreciate is that these are all terms. If you just pick something like 3 to plug in for m, this becomes z to the power of 6. That would be z cubed. Clearly, they're not the same at all. You can't combine those. But when it's written like this, it seems like you should be able to. You can't. All right, and I'm going to go ahead and do 33 as well. This one, you get mn. This one you distribute. Do n times n is n squared. N times negative m is negative mn. Then you add exponents, and the mn terms 0 out. So listen to me. This is wrong. The exponent is supposed to be n squared. And that's subtle, but that's the correct way to write that answer. Because if you wrote this, that technically means this, which is actually equal to this. And 2n is not the same as n squared the last time I checked. So, like I said, we're adding exponents. Our exponent ended up being n squared. You need parentheses around it. The rest you don't need parentheses because the only exponent here was t to the power of. But here they're all the power to a power. But it's not raised. Power to something squared. So. All right. That's that. The worksheet, the rest of it, is due on Friday. Okay? Okay. Now listen, we're talking about exponential functions now. We'll read exponential functions and log functions. We're obviously related. And just put it so you know where we're going with this. We'll do application problems later on of both. Biggest application problem we do is compound interest problems. And after the break, after spring break, that Tuesday we'll have an assessment that's over application problems. And then that Thursday is a test over all of the above. It's like theoretical problems. Nice numbers, in other words. Okay? So that is planned. I forgot I was going to read. Winston Churchill had a lot of good quotes. Obviously, he was a well-spoken man. And then I need to move that slide because it just turned me last period that I don't know, having them, what is the word, juxtaposed like that. It's a good idea. Okay, I remember that. Now, all right, watch. I just want to work a little bit with patterns. You should know your exponent rules already, but what I'm saying is if you memorize them, that's not good. You should learn them by patterns. So here, this is 1, right? How do we know it's not 0 but 1? One thing is because it fits the pattern. Take half of, you get 4. Half of 4 is 2. Half of 2 is 1. And then you keep doing half of. you find that you're getting fractions here. And the thing you're supposed to know is, like here, to the power of negative 3 is the reciprocal of to the power of 3, right? And like I said, if you just memorize all that, that's not good. Same thing applies here. Divide by 3, you eventually get a 1 here. Keep dividing by 3, you get these numbers, which once again are reciprocals of the ones with positive exponents. Okay? A couple other things, just housekeeping kind of things, make sure you're not making silly mistakes. If you want to use a calculator, you better know that the exponent has to happen first, or the addition happens first, I should say. And so if you leave the parentheses off, it won't work. Now, we're trying to determine when you're looking at exponential data and when not. The rule is simply this. If you took any y value, and so this is the y value that comes after this one. So you take y value, divide the one by the one that comes before it, you should get the same constant, always, if it's exponential. So like here, if I take that rule, if I divide 8 by 4, I get the same answer as if I did 4 divided by 2, which is the same as if I did 2 divided by 1. Well, it's the same as if I did 1 divided by half. Because 1 divided by half is the same as 1 times the reciprocal, which is 2. They're all 2. So this is exponential. In fact, it's to the power of x that we're looking at, right? Here, and it's easy to just think of what you're multiplying by, which was 2. Here, what am I multiplying by every time? There is no answer. If you tried to do the same thing, you say, oh, well, 11 over 8, and see if that's the same as 8 over 5, and if that's the same as the next one, it fails. You can check right here. These are not equal, because this way, when you multiply, you get 55. This way, it's 64. It's not the same ratio. And so you're actually adding the same thing every time, right? You're adding 3 every time. That's not exponential data. This one is. Can you tell me what you're multiplying by every time? Yeah, and if you look right here, that's the easiest. What do you multiply 1 by to get this? This, right? And then if you check it, though, 5 halves times 2 fifths is indeed 1. And then if you keep going, 5 halves times 5 halves is 25 over 4. And then multiply by 5 on the numerator, multiply by 2 in the base, you can see the pattern. Okay? So which means that that table is the table for 5 halves to the power of x. All right. Moving on. This you have in your notes. So write this down. And it's talking about the exponential parent function, singular, when in reality it's a whole family of parent functions. Okay? So you have 2 to the power of x, 3 to the power of x, 4 to the power of x. Those are all considered different parent functions. Here, we'll go and graph 2 to the power of x as an example. What I always want is, these 3 inputs. So 2 to the power of 0 is 1, 2 to the power of 1 is 2, and 2 to the power of negative 1 is 1 over 2, reciprocal of 2. And just plot those points. So it goes to the point 1 above the origin, 2 there, 1/2 here. Not a lot of room here. And then to the right, it just grows with that bound. To the left, it's approaching 0. And really, it's going to be a y value of 1/2 and 1/4 and 1/8 and 1/16 and 32nd. So it does approach 0. Now, the main is all the numbers. The range is what? The positives or the non-negatives? It does not include 0, so it's only the positives. Now, here, I just want to remind you, when you ask these questions, we're asking for intervals of increase, intervals of decrease, okay? So what I'm saying is, watch this. When we had a parabola, I had some people say, oh, at 0 it's constant. But 0 is a point. That doesn't count, okay? You can only give me intervals as answers. And the fact is here, as x increases, the y values are always increasing, therefore it is always an increasing function. And just never decreasing, never constant. If it's been decreasing, it's decreasing because as x increases, the y values decrease. I just want to remind you that that's how we phrase it. How's the function behave as x increases? Next thing is an either, obviously. There's no symmetry at all, much less even, y-axis symmetry or origin symmetry. And it is continuous. If it wasn't, I'd want to hear what kind of discontinuity. There's infinite discontinuity jump and removable. But that doesn't apply. All right, just look up here. Like I said, just in general, you should realize that if the base is bigger than 1, then you have a growth function. If it's less than 1, then it's a decay function. Also, you should realize that this I could rewrite as 2 to the power of negative 1 to the power of x, or just 2 to the power of negative x, which means it's really just a horizontal flip of this one. And so you can do it either way. Just graph 1/2 the power of x and say, okay, 1/2 to the power of 0 is 1, 1/2 to the power of 1 is 1/2, and 1/2 to the power of negative 1 is reciprocal, which is 2. And just get those y values directly. Or think of this as your parent function that got flipped over horizontally. Okay? And one more thing about how these behave. Look at this. 6 to the power of x, you think, oh, that's going to be bigger than 3 to the power of x, which is true on the right side. It starts at 1, but then, it'll be 6, 36, 216. It grows, whereas this one only goes, 3, 9, 27. It goes much more slowly. On the other side, though, 6 to the power of x is below. Once you cross over, they do cross and trade places. And it's simple, because think about what I just said. Here, this would be 1/3, 1/9, and so forth, whereas this would be 1/6 and 1/36, so it's going to be smaller. So one of the bigger bases is smaller on the left side. All right, another thing you got to be careful about. And tell me this. Which of these is a negative answer? The one to the right. Like this, of course, if you raise the negative to an even power, you get a positive answer. This, on the other hand, means the opposite of that, which is why it's a negative. They're not the same. So we will never have a negative base. That's what you need to get. This just means a vertical flip, right? And so if I graph negative to the power of x, or the opposite of 2 to the power of x, I'd see a vertical flip, like I said. And then I already said that's a horizontal flip. If you tried graphing a negative base, look at this thing. It would be horrible, atrocious. We never will. You got this using Wolfram Alpha, frankly. Just think of this for a second. If you try plugging in exponents, we would think of integers, and even that's bad. Negative 2 to the power of 1 is negative 2, but then negative 2 to the power of 2 is positive 4. Then it'd be negative 8, positive 16, negative, 32. Positive, you see what I'm saying? It goes negative, positive, negative, positive. That's bad enough. What if you plug in like a half? You should be plugging in a half. But what is negative 2 to the power of 1/2? That would be the square root of negative 2, which is I times square root of 2. It doesn't work. We will never have a negative base. Ever, ever, ever. So, you feel free to play around with this, but I'm serious. If you ever see something like that, the base is not negative 2. The base is 2 with a vertical flip. Okay? Another thing is people mess up this. They think these are equal. Look, the reality is you can have an exponential function times something. That means that's a vertical stretch. Or shrink, depending on what the number is. But this is definitely not true. Just watch. If you're doing 10 to the power of x, let's do that. That's easy. 10 to the power of 0 is 1. And then 10 to the power of 1 is that. 10 to the power of 2. 10 to the power of 3. You're just multiplying with 10 every time, yes? This does not do the same thing at all. What do you get when you plug in 0? 1 times 5 is 5, yes. You plug in 1, you get basically 5 times 2. You plug in 2, you get 4. 5 times 4 is 20. Or in other words, what this really does is starts with a 5 and then doubles and doubles and doubles forever. Which is a totally different pattern from starting with a 1 and multiplying by 10 forever. But people try to do this, and I asked them to graph that, and they draw this, and well, you're wrong. Okay, so be careful about that. That's all I'm saying. All right, let's get to work. Listen, this is really just one of the parent functions. Like I said, it's a whole family of parent functions. That is the parent function of the base of 4. So all I expect you to do is do to the power of 0, the power of 1, and 4 to the power of negative 1 is the reciprocal of 4. At those points. Yeah, the whole way. And just estimate 1/4. There you go. And when you draw, on the left side it's going to approach 0. And once again, make sure you're approaching the asymptote. You can touch. It's going to appear to touch. Just don't cross over. Don't pull away. All right, listen. we're not going to answer all these questions on all these. This one will answer every single one of them. The other ones that I'm going to skip just to get through the notes. The domain is all real numbers, and that's the same as the parent function. The range is also all the positives. Positives only, not zero. Intercepts. Well, this one's easy. It has no x-intercept. The y-intercept is 1, obviously. Asymptotes. And I'll abbreviate that from now on. I mean, like HA is what I normally put for horizontal asymptote. It's just y equals 0. It's the x-axis, right? In behavior, once again, we've done this before. By that I mean as x approaches infinity or negative infinity. As you go to the right, the function values blow up. They go to positive infinity. Whereas you go to the left, and listen carefully, as you go to the left, as x goes towards negative infinity, the y values are always decreasing. But they're not decreasing with that bound. They're approaching what number? 0. And how are they approaching? Well, from above, because we said they're decreasing. They're approaching it, but from above. And once again, we use this notation. You write it as an exponent, but you just put a little plus sign there, indicating it's approaching from above. Okay? And then increasing, decreasing part, distance always increasing. As x increases, the y values increase always. So there you go. Questions? And let's move on. What is that transformation? 5 to the power of x is the parent. Flip how? Horizontally, because this is inside, so it's horizontal flip. And frankly, you don't even need to make a table. You never have to make a table. This one, though, you can easily do without. In other words, you normally would be at 5 above on the right. Instead, you're at 5 on the left. And then normally you'd be at 1/5. Okay, I went too far. Normally you'd be at 1/5 on the left, so you're at 1/5 on the right instead. Like I said, just do a horizontal flip. It's easy. So just watch for a second. You can rewrite the problem if you want to, like this. Because those multiply back to be negative x, don't they? And then, but that means that's 1/5 to the power of x. Because 5 to the power of negative 1 is reciprocal. And you can think of it that way as well. Instead of being the horizontal flip of this, just draw this. And 1/5 to the power 1 is 1/5. And 1/5 to the power negative 1 is reciprocal, which gives you the 5. So you can think of it that way. By the way, on the homework, it has, I don't know if it's the exact same problem. I know it has the exact same base, but it writes it as 0.2. I'm saying I would not deal with decimals. Any decimals they throw at you, I'd write it as a fraction. It was easy. Let's at least do the end behavior. So what is this one? From above. Now if you go to the left, that's when it blows up. The function values go to infinity. Is it increasing or decreasing? Always decreasing. Why? Because as x increases, the y values decrease. Or it's all domain. All right, this one. It's just a shift down 3, right? And listen, you don't have to draw the asymptote if you don't want to, especially if there's a grid. But I would put the plus sign there. The biggest mistake people make with this is when they're trying to draw this, and this is just to the power of x, shifted down 3. I'm going to draw the table, but you don't have to. What I'm saying is they'll put the whole thing going like this. It's like they'll make it go through that point. The parent function does not go through the origin, does it? So it goes through a point 1 above. So when you're done, the point that's normally 1 above the origin is now at -2, 1 above our new origin. And so, okay, I'm going to draw the asymptote because I actually think it helps to have that there. Treat it as your new x-axis, and then you're much less likely to make silly little mistakes. So there, just plot these points as if this is your origin, and you're good. This time, we should write down more of this stuff. The domain is still all real numbers. What's the range? Right? And then the intercepts, that could be tricky here. The y-intercept is easy. It's right there, 0, -2. Which you'll note, this doesn't tell me the y-intercept. That was just the parent function. You gotta look at the graph. Now the x-intercept, that's going to be tricky. So you want to find the x value when y is 0, so set the equation equal to 0. Move the 3 over. And when you solve this thing for x, listen to me. There's two things you need to realize. Like, watch this. They give you these two equations. In this case, to get rid of an exponent, you use radicals. You take square root of both sides. In this case, to get rid of the base, you use logs. Okay? So I'm just saying, you should realize this is a log problem. Really, I'm just going to rewrite it as a log. So it's log base 2, because the base is 2. And the answer is always the exponent. So x is going to go over there, and the 3 is actually the argument. So this is how you rewrite it. Once again, you should realize this base to that exponent should equal this. 2 to the power of x should equal 3, which matches what I've given. But just the simple act of rewriting as a log problem basically solve for x. Now, to give you a little perspective on how big that is, if I do, just watch. 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, right? I'm just saying, log base 2 of 3 apparently is 1 point something. Okay? And so, which means we were pretty accurate here when it should have crossed between 1 and 2 on the x-axis. Okay, we got that. That's the intercepts. Asymptote? What is it? Yeah. And not y equals -2, but y equals -3. Good. And then in behavior, as you go to the right, it just blows up, goes to infinity. The function values increase with that bound. As you go to the left, the function values are approaching what, Hayden? Negative what? -3. Is that what you're saying? Look, the horizontal, that's what I thought. That's sworn that's what it's here. And from above. Use exponent notation. It's not an exponent, but express it that way, which means you already should have parentheses around a negative base. So, yes, the y values are always decreasing, but they never get past -3. They never even get to -3. But they don't stop at -2. A lot of people make the mistake of saying, oh, it's approaching -2. No, it's below. It's -2.9, -2.99, -2.99999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999999. And it's increasing the whole time, obviously. We'll toss that in since we did everything else. All right. Let's get back to your graphing. This one's tricky. Actually, they were nice and gave it to you in the form you want. First of all, rewrite it. And what I want you to appreciate is that you want this form, that they gave it to you in the form you want, okay? In other words, it is a shift left 1, not right 1. Watch. If I had something a little easier to deal with, let's say I gave you this. This does not represent the shift left 10. If you factor out the 2, you'll see it, that you'll be able to interpret correctly. It is in fact a shift left 5. So if you're ever given a combination of the horizontal shift combined with the horizontal stretch or flip or whatever, factor it, and then you'll see what's actually happening. Okay? So I'm saying that this is just a shift left 1. So put your origin left 1, which won't affect the asymptote. And then it's just a horizontal flip. Now, I'm going to make the table and put the flip in there. Although, obviously, you don't really need the table for just a flip. But with the horizontal flip, all the x values would change places. And then you can just plot these points. 0, 1 is going to be 1 above our new origin. 1, comma, third means you're at a third when you're to the right of, and you're at 3 above when you're to the left of the new origin. Listen, where it's really, well, you just may not be sure that you're interpreting correctly. So how could you know and check that you actually do the right graph? Well, just plug in some numbers. And so watch. If we did it wrong, then if you shifted right 1 instead of left 1, then this whole thing would be over here. Right? So let's try 0. If I plug 0 into this, if I plug in 0, I get 1, negative 1. What's 3 to the power of negative 1? In fact, you'd ask for the x-intercepts. So the y-intercept turns out is 0, comma 1/3. Because 3 to the power of negative 1 is 1/3. Which would have told you that that's wrong. If you had the whole thing shift right 1, you'd have the wrong y-intercept. You know, wrong. It's wrong, which it confirms that we were right. Okay, so just plug in numbers. If I try negative 1 in this, I get 0. 3 to the power of 0 is 1, which matches that point right there. I'm saying just do the math. We're just going to graph. Or you know what? Let's do the end behavior one more time. One thing I meant to mention before, here, let me write it out first, is that we use these, we call them behavior statements. You can also write it as using limit notation. Like this bottom one, you can say the limit of our function as x goes to infinity, or negative infinity, I mean, is infinity. And the top statement could have been written as the limit, but I'm writing LIM. Try to make it legible this time. The limit of our function, as x goes to infinity this time, is 0. The thing is, when you do limits, they don't concern themselves with how it approaches the limit. The little plus sign we put, you just don't put it. And so it's almost the same thing, but frankly, we're not going to use that notation. We're going to express it the way we have been, using behavior statements. Okay? If you already wrote it, then you can leave it there. It's practically equivalent. So we'll stick with these. All right, let's get this one done. What's the parent on this? 1/2 the power of x. Saying you need to be able to piece this out. There's your parent. So that means this is the transformation. So what are the transformations? The vertical flip. The negative 2 does 2 things. Vertical flip and vertical stretch, for vertical expansion, by a factor of 2. And it does say, describe the transformation, so you would expect you to write those down. Now, once again, you can do this without a table, but I'm going to make a table for 1/2 the power of x. The power of 0 is 1. 1/2 to the power of 1 is itself. And 1/2 to the power of negative 1 is the reciprocal of 1/2. But then, if you apply these changes, we're going to just multiply the y values by negative 2. And that does the vertical flip and the vertical stretch all in one fell swoop. And then you can just plot the points. There's no shifts, so just draw those points from the origin. So 0, comma negative 2 there. 1, comma negative 1 is here. And negative 1, comma negative 4 is here. But it's not a negative 1. And you're done. And you could have gotten those points without making a table first, with the table to make it easier. Now I want to do the behavior statements in this one because it's the first one that we've had where it's vertical flip. So here, as you go to the right, we're approaching 0 again, but this time from below, yes? So I just wanted one example, which is approaching from below. And then if you go to the left, it's going to negative infinity. Okay? And then we start talking about E. We talked about E before, but look at this. I told you, Euler, well, he didn't discover it. People discovered it when they're doing financial tables. Really, what you're looking at is kind of a really simplified version of the compound interest formula, okay? And so if you take this expression, and what they were trying to do is okay, when I say compound interest, the idea is, you earn interest on your interest. The question is, when do they put the interest into your account? So if they do it like once per year, that wouldn't be good. If they did it once a month, that'd be better. Every day would be even better. Every minute is even better. Continuously would be the best. And so what they did is took the formula and took it to extremes. And so if you did it like once per year, twice per year, and so forth, if this is the number of times per year, then you can see what effect it had on the output. Now, if you take this formula and let's say you start with $1,000, then take this result times 1,000, that gives you your answer, okay? Well, you can see what happened. They found that it was approaching a limit. As you took it into extremes, it kept growing, but not without bound. And so this is what they call E. So it wasn't found by Euler, but he figured out a whole lot of uses for it. So technically, E is what I just showed you. It's the limit of this expression as n goes to infinity. It's like pi. It goes in forever and never repeats. So you don't have to know that. You do need to know that E is around 2.7, right? And this you don't have to know, but frankly, it's a pretty amazing equation. It doesn't seem like much. Frankly, most of the most important things in math are really simple seeming. But this is important because, look, it has 0 and 1 in it, which are very important numbers in math. E, I, and pi are also hugely important. Those are all the most important numbers in math. It has addition and multiplication and exponentiation. All your, your 3 basic operations, all tied up in one equation. That's true. So it's exactly. That's good. All right, look, when we draw this one, we just have to estimate. So E is around 2.7, I said. And, well, here, let's draw our first example. Although I don't want to start with this one. We're going to start with this one. It's just to shift how. Right 3 and up 2. So move your origin, right 3 and up 2. And like I said, I would recommend drawing a new x-axis, or shifting the asymptote. And I'm going to make a table. The power 0 is 1 still. The power, e to the power 1 is e. Let me draw those. 0, 1 is just right there. 1 comma e, you go right 1, and e is 2.7 roughly above the new origin. Except I messed up, didn't I? No, origin's over here. Sorry. 3.7 above the new origin. So that is the right side of our graph. It's going to be 1 over e here. And once again, 1 over 2.7 is between 1 over 2 and 1 over 3. What I'm saying, you should realize it's going to be a little bit below a half. There you go. Okay. And that's it. Get those 3 points drawn accurately and draw the curve accurately, you'll get. Let's go back and do this one now. It's the parent function transformed how? Horizontal, actually do the opposite. Yeah. So that's compression by a factor of 1/3. The opposite of tripling is taking a third of. Which means we need to take a third of our x values. Now you get to, choose which points you put. I want 3 good points plotted. This isn't going to be wonderful because, I mean, we're going to have to estimate those. But the alternative is using, like, if I had x values of 3, that'd be good. But then my y value would be 3 cubed. I mean, e cubed. I don't know what e cubed is. So I'm just going to deal with it. I'm just going to use those numbers and get the graph drawn. And we're just going from the origin. So it'll be right here. Still 0, 1. But then 1/3, e. Go over a third and up 2.7. It should be like in the top left corner of that little square. And it should be, that accurate. And then here, we're going left a third, and up 1 over e is, between the third and a half. So that point should be in the bottom right corner of its square. So it's going to be kind of hard. It'll do. Like I said, those points need to be accurately plotted, as accurate as you can get. Questions? We good? One last thing, look at this. One last thing with the graphing. Just want to appreciate, I said we'll talk about application problems later, but here's, some real world data. What I need to appreciate is that things do grow exponentially. Populations tend to grow exponentially. They can, but not forever. There's always going to be something that stops the growth from continuing on forever. Maybe they run out of resources. Maybe the market drives up. So apparently this happened, but I guarantee it wasn't, or it can't be forever and ever. Your credit card bills, by the way, grow this way. I'm serious. With credit cards, you have 2 choices: pay it off, or have it grow like that. So if you have a bunch of credit cards growing like that, you can go bankrupt from them. That's worst case scenario. A lot of people, they just, they do let it get out of control. People get, $10,000, $20,000 of credit card debt or worse. So anyway, just understand that that's how credit cards work. All right, change gears entirely. Got this front page. Listen, we're talking about solving equations, and this is the simple rule you're supposed to use, and people screw it up all the time because this is the only time where it's true. In other words, what it says is if you have 2 power problems with the same base, 2 problems that are equal that are the same base, then therefore the exponents must be equal. Okay. So you can basically just drop the bases or say the exponents are equal. It doesn't apply like this, where you just have 1 power form equals another. So if it's more than that, anything more than that, you can't do that. Okay? So this doesn't work at all. So here, let's do this one. First of all, 32 is 2 to the power of what? And if you didn't know that, then you should make your chart again. 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5. Okay? But I'm serious. On all these, if you don't know them, just do that chart, and you'll figure it out, but also kind of reestablish it in your mind. You're supposed to know those. And now what do I do? Miriam? I made it look like this, so now I can do what? And there you go. Then we're practically done. And move the 1 over, divide by 3, and we're done. Okay? So there's a nice normal standard problem. Of course, if I change this to like 33, then all of a sudden you couldn't take this approach. That'd be, frankly, a calculus problem. Or a log problem. We'll talk about it later. Now, this one isn't as bad as it seems. What is our first goal? Make them both e to the power of something. Okay? So, this one here, can you tell me what that can be expressed as? E to the power of what? If you see 1 over something, just think reciprocals. So it's just negative exponents. The second one is e to the power of, because you multiply exponents in that case. Now you can combine these. You get e to the power of what? You add exponents, so yes. What you said. And now you're golden. Because now you can just set the exponents equal. And then I'm going to just subtract 2x from both sides. So it zeroes out there. So you get negative 1 there. Negative 9x. Divide by negative 9, you get a ninth. And we're good. Okay? So like I said, really not that horrible. One thing I do want you to appreciate is here, let me put this here again. And what people will do is they'll get to this point, let's say, and then they'll say, oh, well, that means 2x minus 1 equals negative 3x times negative 4x. And no, you can't do that. If you do this, you will not get the same answer at all. You have to get it like this first. And think about it, what did we do here? We added exponents, right? We didn't multiply. That's your clue that this would not work. Now, one more. This is a little different. You get this. For this to work out, what we need to do is express our problem in terms of 3x, or 3 to the power of x. Okay, so here, first of all, if you want a 3, let's replace 9 with 3 to the power of 2, because we can. And then that base can be written as 3 to the power of 4x, right? Well, then I can rearrange it. I can rewrite it as 3 to the power of x to the power of 4. Let me pause. Because what I want you to appreciate is the fact that if you have an exponent that's a product, like we have here, 4 times x, you can rearrange it however you want. In other words, you can put x inside and 4 outside, or you can put the 4 inside and the x outside, because this is 4 times x, this is 4 times x, this is 4x here. I can rearrange it so it's 3 to the power of 2x to the power of 2, because that also multiplies to the same thing, right? And so now, why do I want it this way? Because I know what 3 to the power of x is. So this becomes 1 over 5 to the power of 4. Which, by the way, you're supposed to know. If you don't know it, figure it out real quick. Don't say it if you know it. Do your power of the 5. Basically, everything that was on that chart is the one you're responsible for. And then beyond that, and I won't require it. So I'm saying this is 125, and then what? And you're supposed to know that, so I expect you to write it. If it had been like 5 to the power of 10, I would just leave 1 over 5 to the power of 10. Okay? If you don't have the calculator, just leave it. And frankly, if it's too big, like 1 over... Even if you do have the calculator, leave it like that. It'd be really, yeah, I don't want to write that many digits. And I don't want to, frankly, I don't want to check your digits. As horrible as that. There you go.